In this video, we will calculate molarity, which is a way of expressing the concentration of a solution, calculated as moles of solute per liter of solution. So for example, if we say that we have a 1.0 molar sodium chloride solution, which is how we read that. When you see like the 1.0 m, it means like molarity, but we read it as 1.0 molar sodium chloride solution. It would contain 1 mole of sodium chloride dissolved in enough water to make 1 liter of solution. We know then that sodium chloride is a strong electrolyte. So what's really happening then is I've got my sodium chloride, and when I say that it's a sodium chloride solution, aqueous, I really mean that it has totally dissociated to form +1 sodium ions and -1 chlorine ions. And we put those in as aqueous, as now they are totally covered with their little shells of water molecules. That's really what's in a sodium chloride solution. It's sodium and chlorine ions. So if I started with 1 mole of sodium chloride solid, I put that in enough water to make a liter of solution. In the end, as it totally dissociates, I would get 1 mole of sodium ions and 1 mole of chlorine ions. Does that kind of make sense? And it's not that sodium chloride ever exists as a molecule, because ionics are big crystals where it's oppositely charged ions in this repeating crystal pattern. But if you think about it as sodium chloride originally was a 1-to-1 ratio of sodium and chlorine ions, and now they're just going to split. So for every 1 mole of solid sodium chloride, I would really be splitting fully to form 1 mole of sodium ions and 1 mole of chlorine ions. All right, let's do some calculations. Let's bring on the math. So if we want to calculate the molarity of a solution prepared by dissolving 11.5 grams of sodium hydroxide in enough water to make 500 milliliters of solution, well, we're going to use this little equation, molarity equals moles per liter. And these are really, really common calculations in that often we're using solutions in the lab, and we either need to make the solutions ahead of time, or maybe we need to know how much solution to use. And this is our guy. Molarity is moles per liter, which means then that if I measure by mass, which we always do in the lab, if I have 11.5 grams, I'm going to need to turn that into moles. So step 1, 11.5 grams of sodium hydroxide. And now for a while, I know that sodium is a +1 ion. I can find that on my periodic table. We haven't had to use the polyatomics for a while. And so it may take a minute to look them up and make sure that we've got the right formula of the polyatomic and we've got the right charge. But there's a chart earlier in here, that solubility table, and that's got a lot of the common polyatomics on there. So hydroxide is OH -1. And the more you use some of these common polyatomics, the more, like, we're just going to know hydroxide is -1. That's really, really common. And it's neutral. So I can get right after it. I want to cancel grams, put her into moles. 1 mole has the mass on my periodic table. And we're not going to do a ton of rounding here. When I'm using the periodic table in the AP packet, if it's multiple choice, obviously you can round all day long and nobody's going to know. But if it's free response, then just leave everything as is. Sodium and oxygen and hydrogen. I'm going to say about 39.99 grams. Now, if this were multiple choice, that's 40 all day long. I'm going to say like 23 for the sodium, 16 for the oxygen, and 1 more for the hydrogen. But if it's free response, then I'm going to leave a little more precision. Okay, so we're going to plug this in. And now for sig figs. I'm going to go back to the original given data. So the original given number was 11.5 grams. That's 3 sig figs. So I'm going to leave 3,288 moles of sodium hydroxide. There we go. And so, yeah, and with the molar mass, I'm just going to leave whatever's on my periodic table, just so that in the end, maybe my answer is as precise as possible. But when it comes time to rounding for my final answer, then I'm going to go back to the data given. All right, so we got moles, and now we're ready to go. Molarity is moles per liter. Now, I see this is 500 milliliters, but it does need to be moles per liter. So I'm going to have to switch that. So I take my 500, and I'm assuming that they meant for that to be precise. Let's put a decimal in there. And then I'm going to move it back 1, 2, 3 to switch this to 0.5 liters, which again is a really common issue, and that often in the lab I don't maybe need a full liter of solution, but when I do my calculation, it does need to be in liters. Alrighty, so we plug this in, and again, I'm going to go 3 sig figs with the original data. Let's, boom, assume that was meant to be precise, and I get about 0.576 molar. NaOH. That's not so bad, right? It's a plug and chug kind of equation. You maybe used it last year a little bit. Moles per liter. And this is all really, really common, that we may need to switch our mass to grams, and maybe we don't have a full liter of solution. Other ways that we can twist and turn this little equation. Give the concentration of each ion in the following solutions, which there's just one. Okay, so now this is meant to be really simple, but something that we're going to end up having to use quite a bit. Cobalt-2 nitrate, cobalt. The Roman numeral means that it's +2. Nitrate is NO3 -1. Now again, nitrate is a really, really, really common polyatomic, and eventually you'll just know it. But it's been a while since we've had to write a lot of formulas and use these polyatomics. So if you've just flipped back a little bit, they're on that solubility table. I mean, most of them that we'll run into are on there. And so for a while, if you got to look it up, there's no harm in that. I need 2 nitrates to make this neutral, +2 -2. Okay, so we have a 0.5 molar cobalt-2 nitrate solution, which does mean that it's aqueous. It was solid cobalt nitrate, get rid of this, and then we dissolved it in water. When it's in solution, nitrates are 100% soluble, so it's going to dissociate. It'll dissociate to form ions. I'll get a cobalt +2 ion, and then we would write this as 2 individual nitrate -1 ions. When I have the parentheses and the little subscript 2, that means that the 2 nitrates are like bonded together in the original compound, but now they're all going to split. So by putting the 2 out in front as a coefficient, I mean that it's 2 individual nitrate ions. And we can still put in a Q. They would be in solution covered with water molecules. Okay, so now the original solution was 0.5 molar, which just means like moles per liter. There was 0.5 moles of cobalt nitrate per liter of solution. Well, when that thing dissociates, you're going to get 1 mole of cobalt for every mole of cobalt nitrate. So this should be a 1-to-1 ratio. Molarity, or you can say moles per liter. But then I get 2 nitrate ions. Ready for the difficult math? 1.0 moles per liter. And so eventually we might want to just study the nitrate. How many moles of nitrate should be in this solution. And then we have to kind of think about the ratio in what's happening when that original solid dissolves. That, oh, I had 0.5 moles of cobalt nitrate originally, but really when that's in solution, I'm going to get 1 mole of nitrate ions. So we're just concerned with the ratio of particles. That's it. That's all we had to do for that one. Oh, that's easy. I can handle that. Now here's maybe a way that I could use that. How many moles of chlorine ions are in 1.75 liters of a 1 times 10 to the negative third molar zinc 2 chloride solution? Okay, so I want to know how many moles of chlorine ions are in this solution. Okay, well, let's see what we got here. We have the molarity, 1.0 times 10 to the negative third molar zinc 2 chloride. So zinc is plus 2, chlorine, well, that I can look up on my periodic table. Boop, boop, boop. Minus 1. So to make that neutral, I need 2 chlorine. Okay, so I've got the concentration, I've got the formula, and the other thing I'm given is the volume. So molarity equals, let's solve this sucker for moles. And I do have volume, and it is in liters. So I can cross multiply, solve this thing for moles. About 0 points. Oh, let's see. Should we go 1 or 2, 3? Let's go 3 sig figs here. 0.00175. And that's moles of the zinc chloride. Trying to decide like 2, 3 sig figs. I mean, either is fine. Technically, if you're within plus or minus 1, you are in range of full credit. I'll leave the 175. I don't know if I want to round that to 1.8 quite yet. Cool. Okay, so now that's moles of the zinc chloride. But the question is really saying how many moles of chlorine ions are present. And so eventually you'll get so good at this that you don't really have to write anything out. You'll just do it in your head. But here's kind of what's happening. The zinc chloride is now in solution. So it dissociates to give me a zinc ion. And then I would write this as 2 chlorine ions minus 1. These guys are still swimming around in the solution with their shells of water molecules. And so I really just need to think about the ratios. That if I had 0.00175 moles of the zinc chloride per liter now, it's going to give me 0.00175 moles of zinc ions per liter, but then twice as much chlorine. So if I multiply that by 2, 0.0035 moles of chlorine per liter of solution. Oh, look at that. And that's it. There's my answer. I'm looking at the 0.0035 moles. And then we're done. So again, you probably wouldn't even have to write any of that in the end. That I would look at this number and say, okay, well, that was moles of the zinc chloride. For every mole of zinc chloride, there's 2 moles of chlorine. So I'm just going to take this guy and multiply by 2 to get moles of chlorine ions.